Hi, welcome to my channel. I'm so thrilled that you are here with me. In the last video, I started with transistors, PMOS, NMOS, then I started talking about inverter, NAND, then AND. And my plan is to, show you inverter, NOR, OR, flip-flops, latches. Those are the basic building blocks in physical design. But what I was thinking of, instead of I take you through those basics first, it's important that I step back and explain what is system on chip, then what is physical design, and then when we talk about physical design, why these standard cells or these gates like inverter, buffer, they're very important. So let me start with system on chip. Today's videos will be more about system on chip. And once I have these higher level things covered, I'll go to the deeper gates level again. When we put a system of electronics on a chip, that is literally a system on chip. Okay, what is contained in a system? What we call a system? Any system? And what are those components of a system? So here is my definition. Different people can have different definitions. Okay, and system can be anything. System is a system of electronics that is able to interact with the environment and process the data in a way that the system wants to do, that or we want from system to do. Okay, so here are the components of a system on chip in my definitions. So let me take you through some drawing that I'll do on iPad. I'll share the screen of iPad. First component of a system on chip is a CPU, central processing unit. CPU is the brain of the system. It makes decisions like our brain. Okay, a CPU can consist of several cores. Those basic cells of processing elements can be example of those cores is Atom core from Intel, Intel Xeon core, then ARM core. Okay, so one CPU may contain one or several 20, 30, 40, depends on how powerful we want to make a system. So first thing is CPU. Okay, and as I said, a CPU can have different cores. Let's see, we have in our example 6 cores. Okay. Within each of these cores, we have the basic elements that are able to do logical or arithmetic operation. Then there is always some on-chip memory within the core as well. Okay, so those components are inside arithmetic logic unit and some on-chip. Let's say the bottom one is some on-chip memory in all of those. Okay, so that is one component. The second component is what I call IOs. Okay, it's like our body. We have hands, legs, nose to smell, eyes, ear. Okay, these are all our inputs and outputs. Using these IOs, okay, we sense data. We take the data as input, and also, as if brain decide that we have to do some action, then brain also send those signals to our hands or our legs or other parts of the body. Okay, so an IO is an input and output. So IOs. Within each IO, now in terms of system on chip, the example of IO is a USB port, interface to hard disk, a VGA port, an HDMI port, an Ethernet port. These are all the IOs. For each IO, you have two components. Let's look at this. There is one analog component and the other one is a digital component. Analog component is connected to, think of this is USB. Okay. USB data comes, it goes over the cable, so it's an analog signal. Okay. It comes and it is processed with whether input or output by the analog module. Analog, the most of the processing or the controller part is in the digital. So that controller, which is D here, okay, the control makes all kind of decision or processing of information. It's just when it needs to send data or when it needs to get data, it interacts through the analog component onto the main IO. So this is our actual device. Okay, interface. Okay, and then this together, A and D, is our one IO. So this whole thing is one IO, digital, analog, and actual port. We will have several of these type. Okay, so this one is for USB. We will have one for hard disk. Okay. We'll have one for display. We'll have one for Ethernet. We might have a PCI slot. Might have some other specific port that that depends on a particular system. Okay. These are the, I just put a 6 example of IOs. So we have 6 core, we have 6 IOs. The third one is an accelerator. Okay, I was thinking of the memory first, but as one of the IOs can also be way to access external memory, like a DDR you connect to it. So those can be also part of the IOs. Okay, but the third thing that I can consider important in today's system on chips is what we call accelerator. Job of the CPU is, as I said, is the brain of the system. Whenever an input comes, some signal it senses on, say, a USB. Okay, a signal will go to CPU that, hey, there is some data here on this IO. Okay, so the CPU or core will come, fetches that data, put that in the memory. Okay, and once the memory is there, then later on some other cores, the same core, can take that data, process it, and when we need to send it, then it will put that back into this IO and it will go out. And some processing in this whole process then CPU needs to do, each core will do that. So that is the job of a CPU. I mean, there's a one IO. We can have at the same time 6 different IOs requiring data as input and needs to be processed, or some data already processed in the memory that need to be sent out. So CPU is busy doing that. Now let's say our system on chip that we are creating is for a video processing application, where we know that while we have some USB available, maybe mouse connected or some other device connected, and maybe we have a video going out as display data going out to, or data going to in another HDMI or PCI. But at the same time it's a video system, so it will have somewhere a continuous stream of video coming in. Okay, so what we want is, if there are certain function on videos, say let's say we need to apply some filters, we need to do some other video processing algorithm that we need to run on the video, and that thing will continuously run. So what we don't want are these cores is are that these also get busy with that video, because once these are busy with that filters or other video processing, then these will always be busy on doing that, and may not have time to do other applications or to do other jobs that probably be happening on these IOs. So for that, if a system is used for a video application heavily, then we have a helping hardware. Okay, that hardware could be another very targeted processor, or can be some other piece of hardware which can really operate certain operations, perform certain operations on the video input. So that helping hardware is called accelerator. Okay, it accelerates that processing of that information without the need of CPU or cores being involved all the time. Okay, an example of in the networking, for example, compression, decompression, or running other security algorithm is one example of an accelerator that we need for a system on chip that's going to be used in networking. We can have, if we have a system on chip for automotive, we might need an artificial intelligence processor and hardware that could be doing all the work at the same time. So those are examples of accelerators. Okay, so these are the three pieces of hardware that will be there in a system on chip. Okay, then what happens is all these cores, okay, they are connected to each other. Okay, I mean, they can talk to each other, help each other process, send data to one core or fetch from the memory using different cores combinations. Then cores also need an access to, let's say, all these cores need to talk to these IPs, and IPs need to talk to each other in some way in case they need to share something. Then you have accelerator. Okay, accelerator can be also several pieces of hardware. Okay, let's say you have one security one a particular filter, another one does another filtering, or different other operations. Okay, so let's say different blocks with an accelerator exist here. Okay, so then this whole network also need to talk to this in case they need to send information to an IO, or they need to talk to CPUs. Okay, so that they're able to send that over. So the whole thing is talking to each other. This thing is a network between different processing elements that is also called a network on chip. So in a system on chip, we have all these individual components, and the person or the group who creates that system on chip also need to connect all these things together. Okay, so next thing is, each of these, let's take an example of an IO. Okay. When we make a system on chip, Okay, we don't have to create everything in-house. There are some things which we have good expertise on and we can create within our team. But it's less likely that we in a team there will be expertise to create every IPs. You don't also want to create all the IPs because you want to quickly put things together, make it working for a particular application, and develop a chip for that. You don't have enough investment to have design teams creating all these, and you don't also want to take a bigger risk of creating everything from scratch. And what if those things, typically an IP takes time and go through some revision of silicon become before it becomes more stable. So it's not very favorable for a system on chip team to have everything within house. So why not use expertise of some other teams? Maybe there's one team who is super good in creating a USB controller. Okay, you can take a finished hardware from there. So let's say another company, outsource company one, they create very good IPs, proven IPs, high quality, high performance, or performance power, whatever we need for that IP. So we take from there. Okay, this is a finished hardware, finished layout. So all we need to do is take a verified thing, put in our configuration, and we don't have to worry about inside of it. We do only have to worry about on its interface. That's one example. Then there's another IP2 that take another color, IP2 that we need to create. Maybe there's IP6 that we need to create. Maybe there are different components within Accelerator that we need to create. There's IP7, there's IP8. Okay, let's say we take code from somewhere else. So it's already a finished design, a layout verified. And these blocks, which are already finished and delivered by another company, these are, we typically call them macros or hard IPs, okay, HIPs. These are the IPs that we create ourselves, or maybe we create from another company, but we can create a layout ourselves. Can be called soft IPs or IPs. Okay, soft IP is the one created by another team. It's in software, it's not converted into hardware or layout, so it's our job to do that. Okay, let's say this IP. What is that? Let's call it 10. This is soft IP. Okay, then we also have in-house development, and that's we call an IP there. Okay. These are the different building blocks. I'm not going into too much detail within each, but at a higher level, these are the basic building blocks. Each of these, let's say one IP. Okay, it's a large hardware. Okay, maybe this one is 1 million gates. Again, I'm measuring the size in terms of NAND cells, and in terms of transistor, one NAND has 4, so I can say, okay, it has 4 million transistors. Then each of these can be 4 or 12, 8, 10 million transistors. Okay, and overall our system on chip, we have seen like in billions transistors. So it's not possible for a designer, okay, to work at a transistor level and create this system. It's simply not possible. It's gonna take years and years. Okay. So instead of working with each transistor, designers of SoC, they work at gates level. The people who create the hardware for this, are called physical design engineers. Okay, so the physical design is the process of creating a hardware, a layout from a higher level description of the hardware, which is called RTL. Okay, so an RTL is a, let's put another one. Okay. As I said, it's a big hardware. We cannot create a schematic of transistors and start simulating them, verifying our circuit. Instead, what we do is we create a hardware in a hardware description language, which is HDL. And these languages are called Verilog or VHDL or System Verilog. And these languages give us a good way to develop that hardware at a much higher level in terms of typical language construct like if, else, case statements, and some other constructs. Every language will be different in terms of making different components, but really like a C language, you can create a flop, you can create a latch, you can create an operation, NAND, or other state machines. You can create in that. Okay, so that thing is RTL, register transfer language. It can be Verilog, VHDL, or system Verilog. So that IP that I explained before, its digital part is written in RTL. Okay, and its analog is designed in the form of transistors. Okay, so analog part will be smaller. RTL or digital portion will be in millions of transistors, and here we talk about maybe hundreds of transistors. But once you have an RTL, okay, you need to convert that RTL eventually in form of transistors. Transistor and interconnection of transistors. In the previous video, I used some schematic for PMOS. So this RTL needs to be converted into transistor, and the tools, the process, the flow that we go through to create these transistors is called physical design. Okay. Within physical design, okay, instead of working directly at transistor level, okay, we have another, we work at a bit higher level. Okay, so we work at gates, or we call cells as well. Okay, so we work at one level up. These gates or cells are inverter, NAND, and flop, latch, and all those. Okay, so the RTL is converted first into these gates, and each gate's already a finished layout. I'll go into details of that, because in the last video I started talking about these different gates. So that's why I started with these gates, inverter and NAND, and it's important to understand the structure of those, because as a physical design engineer, you will be working with tools who are going to optimize the placement, interconnection, routing of all these gates. Hold your RTL, okay, will be converted into gates. Let's look into an example of that. Let's see. Sorry. Yeah, take a look at this one. This is Let me take a pointer here. Okay, 1 second. Yeah. So if you look at this piece over here is an RTL. Um, this is a construct in Verilog always, A and B are input, S is select input, and it says that when select input is 0, you move A signal to the output, and when it is 1, you may move B into Q. Okay, so this is the RTL description. Okay, so RTL designers don't have to really create a hardware or talk about transistor or standard cells or gears. So they really work at pretty high level in the form of these constructs. Now, physical design engineers, they will convert this RTL into a netlist. Netlist is a connection of different gates. For example, in this one you see there's an inverter, there's an AND, two ANDs, and an OR. So this hardware, in the of RTL is converted into an equivalent actual hardware in the form of AND and NANDs. So this conversion is really what the physical design is. So that's why in my previous video I started talking about AND NAND inverters, and these gates are also called standard cell. So the physical design is the process which is a standard cell based, and it work on the optimization and verification of those gates. So I think that is good for today. Hope I'm able to give some different ideas on physical design and system on chip. In the next videos I will go further into these AND gates. We look at the transistor a little bit more. What is the technology? 10 nanometers, 7 nanometer, 32 nanometer, 22 nanometer. What are those? And after going through some of those basics, we can, I believe, go on to physical design and look into what components within physical design and what are different steps to transform an input RTL into a finished layout, which we send it to the fabrication plant. Okay, so stay safe. Thanks so much for watching. See you next time. Bye bye.